Hi, that's Mr. Carson again, and we're going to look at radicals today. This is a very important part of the course, especially as it links several parts together. And as we're going to see, we're going to try to relate it to the whole idea of ozone depletion. Now, before we start, I think we need to know what a radical is. And in terms of chemistry, it refers to any really super reactive species. Now, in most of the terms, it will be an atom that is not quite satisfied, particularly a non-metallic atom. But it can be a molecule or a part of a molecule that requires some more electrons or requires something to attain stability. Now, these things are typical and they react with another radical in the reaction, and they keep on reacting until the radical itself disappears. Now, it disappears in a very interesting way, as we'll see a bit further down the track. And the reaction involving radicals will keep on going and going until the last radical is removed from the system. And this is why we refer to it as a chain reaction. Now, in chemistry, it sounds pretty funny to have chain reactions. We normally associate chain reactions with physics, but it's not really too much of a difference. What it basically means is one part triggers something more to happen, which then has a cascading effect on the rest of the chemicals. Now, the best example we've got is the ozone depletion, and it's using the CFCs. And as we're going to see, radical formation involves some basics in bonding and understanding atoms and understanding electronegativities and the needs of atoms. Right. A chain reaction is a little like when we have something that is produced and then goes on to cause another reaction to happen. And so we normally say we have to initiate or start a reaction. And once we start by forming the radical, then the rest of the reactions will proceed by themselves. And as we see down here, you're going to be asked this in the test. It's quite a common examination question where they will ask you to provide an example of initiation, an example of propagation, an example of termination. So obviously they go with the ideas. Initiation is going to be the formation of the radical. Propagation is the radical going on to cause the chain reaction. And termination is when we remove the radical from the situation or from the reaction vessel. It's best if we look back at UV and the whole idea of CFCs. Now, as we can see in this, I've obviously taken this from the internet, and it was a nice clear introduction to the whole idea of CFCs and the chain reaction and radical formation. Right, we see in this case we've got a single carbon with one fluorine and three chlorines around it. Now, all of the bonds between the chlorine and the carbon and the fluorine of the carbon will be polar because of the high electronegativities of the halogen. So if we get the right amount of energy, and this is provided by UV light, remember that radiation, the energy carried by radiation, is proportional to its frequency, or if you like, and that is related to its wavelength. So we can say the shorter wavelengths, like UV, have higher energy than normal light, the visible light spectrum or heat. So what we're trying to do is to try to break free one of these atoms. And UV light at certain times of the year in the polar regions is able to do this. And we get a chlorine radical forming. Right, now the chlorine radical then goes to the ozone molecule. Now, as we know with ozone, it has a double bond between two oxygens, and then we have a coordinate covalent or dative bond formed with a third oxygen. So the radical is able to break the bond. Obviously, the double bond has more energy and requires more energy to break than the single dative bond. So what the chlorine does is it ducks into the molecule and breaks that bond and takes away one of the oxygen atoms. This leaves an oxygen molecule in there, and we still have a radical formed. We still have free radicals floating around. Now, this then keeps going, and as we form more oxygen atoms, which is basically what happens in ozone depletion. Ozone is converted to oxygen. And the chlorine is a free radical, so it can go on and cause more damage to the ozone molecules that are there. And so it just keeps going and going and going until that free chlorine atom, or the chlorine radical, is tied up somehow. So let's look at this one. And it talks about initiation in terms of homolytic bond cleavage. Homolytic bond cleavage means that we have two bonds, or a molecule that contains two of the same atoms. So like a chlorine molecule. So in this case, there's even amount of pull on it, so it's a non-polar bond in this stage, as opposed to a heterolytic bond cleavage, which would be something like the carbon-chlorine bond we saw before. So we have this polarity of bond, and we have something that wants to break the bond because of the high electronegative nature of the halogen. And so UV has just enough radiation, has just enough energy to actually form the radical. So this would be called the initiation phase. So the sample here is I've given you an equation involving a homolytic fusion of these. Now we see that when we start, we don't have a radical at all. But with enough UV light, or the UV light of the correct wavelength or frequency, we break the bond between the chlorine atoms, and we actually form individual atoms, and these are radicals. So we can start off with 0 radicals, and I like actually the way this diagram does it. It talks about the number of radicals that are available in the system. So we start off with 0, and just with the homolytic fusion, we actually get there. Fission, we actually get there and have 2 chlorine radicals. All right, so initiation causes radicals to enter the system. Propagation has the radicals then causing further reactions. And normally we form more radicals in this, and they keep then pushing on and on and on. So the example we're going to use is this chlorine radical coming next to a methane molecule. All right. Now we see in this that one of the hydrogen bonds with the carbon will be broken. So the chlorine radical steals one of the hydrogens. This leaves carbon short of electrons. So we can see we've got a CH3 radical forming. So the number of radicals remains unchanged. All we've done is just moved around some bonds a little bit. Now this could happen in any sort of a structure. We've seen, if you wanted to relate it back to ozone, you would see the Cl radical coming into the O3, forming the ClO, right, and the O2. We still keep the radical formation. The ClO, does oxygen have enough electrons? Think about it. Right, so then we can have other things going on. This CH3 radical, in this case I've got shown, goes to another chlorine, and it could be any other sort of a bond. Goes to another chlorine and breaks it apart. One of the chlorine atoms attaches itself to the CH3 radical and becomes a CH3Cl, which is a lovely little compound, chloromethane. And what's left over is a chlorine radical. So we still have radicals. Notice in the product, under the product, in both these situations, the number of free radicals is not 0. So we've still got this going. Finally, we can have termination. Now, termination basically involves combining of radicals to form a less reactive compound, as I've said here. So in our example, we are going to simply put these two radicals together, the chlorine radical and the CH3 radical, to form that structure. Notice that we started off with 2 free radicals and end up with 0. Now, this is a very simplistic view of radicals and the chemistry involved, but you are going to be tested on this in your exams and in your unit tests on this whole process.